Thank you, Nicole. So Nicole has asked me to kind of give an update about where we sit with spatial repellents. Originally, we had a concept of what spatial repellents were. We had the thought that they acted in a certain way. There was a limit as to what they could do. And over time, a number of groups, including ours, have been doing research in the lab, in the field, and finding that the actions of these chemicals that we call spatial repellents go far beyond just breaking the human vector contact from a behavioral standpoint. There are a lot of actions that occur that may impact on every aspect of the life stage of the mosquito. So I'm going to be covering a little bit of that, but what I want to do is start out by kind of going through where we started out. And I remember in the early days, 20, 25 years ago, there were heated discussions about what are the actions of these chemicals? What are they doing to the mosquito? And people would argue that there's excitorepellency, all these different actions, but all centered around either movement away from a host source without making contact, which we called spatial repellency, contact irritancy, which was more of making contact with a surface that had the chemical. The mosquito became irritated or agitated and flew away. And then we looked at toxicity. So early on, we limited it to just those three main behavioral actions. And that led to us developing these crude models. If we were to have a house, we protected it with a spatial repellent, we could exclude a large number of mosquitoes and basically create a bubble around that house, protecting everybody within that structure. Anything that did come in that broke through the spatial repellent barrier would then maybe make contact with the surfaces, become irritated, and leave before feeding, and that would be the ideal situation. Then we would have toxicity where the mosquito would become overcome by the vapors, or they would leave and die, or some of them might actually survive, which would be the least acceptable situation. So with that in mind, we were called to WHO to develop the spatial repellent test guidelines. And in doing that, we had to come up with a number of assays that we liked to use for selecting out these various endpoints, entomological endpoints. But we struggled with what the true definition of a spatial repellent should be. And we settled there on a large number of behaviors, but anything that basically prevented biting. So a reduction in biting was what we were really looking for. But a lot of things can result to a reduction in biting, including toxicity. So that's where we ended with these test guidelines. But if you look at that, the current definition is focused on one point in time in a very crude life cycle of the mosquito. But it's at a single point in time. But over the years, what we've seen is that all of the publications that have been generated, we're increasing the number of publications, and all of that data is showing us is that this is not a single point in time event, that it extends beyond the initial exposure, that we're getting post-exposure events that are disrupting a lot of the life cycle of the mosquito. So this is a diagram of the transmission dynamics David Smith et al. Published, and you can see the complexity of it. You've got seasonal patterns, you've got egg laying, you've got all the different components that go into the transmission dynamics of some of these diseases. And as our view of the transmission dynamics of these diseases change, so must the view of these various chemicals that we're using and these various tools that we're using to interact with various aspects of this diagram. We need to look at spatial repellents from the standpoint of not being a sole point-in-time exposure. We have products now that we put out, and they're exposing the mosquitoes on a nightly basis to a spatial repellent dose. So these are sublethal concentrations. We're looking at various aspects of the life cycle that we're targeting that we didn't target initially with our spatial repellent concept. So if you look at some of our early work, we developed an assay. We could tease out doses that were considered spatial repellent, that were not killing the mosquito, and then it moved into a toxic level where we were killing the mosquito. But within that range of doses that actually did not kill but repelled, you might have impacts on emergence, mating, sugar feeding, all of the life strategy characteristics of a mosquito And those are the things that we wanted to start to look at. How would these behavior-modifying compounds impact on these other aspects of a mosquito's life cycle? So some of the early work by one of our graduate students, Joe Wagman, showed that it wasn't an initial impact on the mosquito. If you exposed a mosquito to a repellent, it just didn't fly away. That impact lasted far longer than just that initial exposure to the compound. So he found, what he tried to do was select mosquitoes on day 1 and show that he could repeat that on day 2 and then follow it up with a day 3 trial. So the repellent effect occurred on time 0. He saw an attenuation of that result 24 hours later. When he repeated with the same mosquitoes 48 hours later, that repellent effect returned. So that got us thinking, was how long were these effects actually impacting on the mosquito? So we set up a trial where we exposed mosquitoes, put them in a feeding arena, and looked to see at various time points, 1 hour, 3 hours, 6 hours, 12, 24, to see how long could we actually disrupt the feeding behavior of the mosquito. And what we found was that, similar to what Joe found, was that out to 24 hours, we were still having an impact on those mosquitoes by seeing a reduction in feeding. It was only a 12% reduction, but it was still significant as compared to control. So these reactions that we're seeing are going far beyond just that initial point of contact of the mosquito with the repellent. Then we started to look at other things. We started noticing in our test arenas that the mosquitoes were showing some form of agitated flight. They were moving much faster, they were buzzing around, they weren't resting as much. So in the early days, we set them up on flight mills. We would expose the mosquito, attach them to a pin, and then allow them to fly around in these flight mills. We would register flight distance, flight speed. And what we found was that a mosquito that interacted with transfluthrin actually flew farther, but that was a result of them flying faster. These mosquitoes were much more agitated. They were flying. They were just buzzing around and not being settled. But we also found if we looked at it 1 hour post-exposure, that trend reversed. And then 3 hours as well, that trend stayed the same. So what that tells us is that somehow those mosquitoes, the flight reserve, the energy reserves of those mosquitoes are actually being depleted, and they're actually slowing down. They're almost exhausting themselves with this agitated flight. So nowadays we can do a lot more. We can do a lot more detailed studies because we've got behavior tracking software. The top study, Phil McCall's work, where they're doing the flight around a bed net, how many contacts it makes, so they can monitor resting, they can monitor flight activity, all the different various endpoints that we couldn't measure with just the flight mill. In the bottom is the work that we've been doing and looking at different arenas with treated versus untreated mosquitoes. And again, we can look at number of turns, we can look at time resting. And the same thing that we saw in our flight mill is repeated here, where you see the transfluthrin exposed mosquitoes actually show a much higher level of activity. They're not resting as much, they're just buzzing around a lot more, they're making a lot more turns. So again, showing that kind of exhaustive behavior which is impacting on the mosquito. So we're seeing this hyperactive response with transfluthrin. It's exhausting the reserves. But one of the questions that we had is this actually impacting on the survival of the mosquito? And what we found is if we treated cohorts and carried them out for the full length of the lifespan of the mosquito versus a control population, we saw that with Aedes aegypti, we actually saw a reduction of 4 days in life as compared to the control. And with Anopheles gambiae, we saw a 3-day reduction in the lifespan. Now, it doesn't seem like much, but when you give this data to the modelers, it has a huge impact on the transmission potential for these mosquitoes. So when we think about spatial repellents, we need to go beyond that initial single-point contact of the mosquito with the repellent in the huts. Christopher Bibbs this year actually published some data on some great studies on the egg production of mosquitoes. He found that if you expose mosquitoes to transfluthrin, Aedes aegypti, you actually had egg collapse with the resulting eggs. For the ovaries, he found fewer numbers of eggs were actually produced in the ovaries, and those that were produced showed an increase in melanization, which actually reduced the egg viability. So there's a lot going on with this something like transfluthrin, and he even stated in his paper that this is a single point contact with transfluthrin. These chemicals are out there in the environment. They're making multiple contacts. So this may actually be accentuated with some of the strategies that we're using today. We carried out a study looking at the potential for disrupting ovipositional attraction. And our assumption was that if you expose mosquitoes to transfluthrin, they would be confused and they wouldn't find the containers that held ovipositional attractants. But what we found was the opposite. The mosquitoes actually went to a greater extent to those containers with the attractants. And our assumption here, we're still teasing this out, but our assumption is that there's a heightened response in the mosquito or a heightened sensation in the mosquito to olfactory cues such as ovipositional attractants. The other thing that we're looking at here that we've actually noticed in recent years is a phototactic response, a higher sensation for light. And so mosquitoes are actually going more preferentially to light sources. This may actually help us with traps. So the light traps that we're using, could we implement this in a push-pull strategy? So if you look at what's been going on, we're starting to see a lot more emphasis on these post-exposure effects, kind of delineating what needs to be done in terms of our gaps in our knowledge around spatial repellents, in terms of diversion, formats for chemicals, and we're building that breadth of data around what needs to be done if we're going to have it truly a spatial repellent compound for WHO recommendation. But in conclusion here, some of the things that we're talking about, we really need to consider. Most studies have been done with a single dose, and some of the products that we're using now in the field are 1 month in duration. So if a mosquito cannot obtain a blood meal on night 1, what happens on night 2? Does it come back? We're suggesting probably not. There seems to be that delayed response in coming back for a secondary feed. So even if it comes back every other night or every third night, it's still picking up multiple exposures to these chemicals. And we're seeing from some of the other studies that that's impacting greatly on egg production, egg viability, just all of the factors that we really consider as key transmission issues with these vector-borne diseases. Most of these studies have been done with transfluthrin. This is a volatile pyrethroid. So we know that it's going to have an impact as a toxicant at some level. But what happens when we're looking at things like PMD, other things that we consider as repellents? Are those going to also show similar types of trends? Or are they going to show completely different types of impacts on the vector behavior, all of these other endpoints that we've been measuring? So we need to do much more studies on these other types of active ingredients. The broader vision, we need to look at how these different types of interactions are complementing or interfering with some of the other technologies that we're using. Like I said, phototactic response, we're seeing some issues around increased attraction to light. Can we utilize that for push-pull systems? Can we use the ovipositional attractant data that we have about increased attraction to make some of our traps, our ovitraps, better, for our GATT traps, increasing trap collections? And then what are the considerations that we need to have about how do we evaluate these tools now? We developed these guidelines, and we had a small set of tools that we were using to evaluate them. Do we need to increase that suite of tools to take into account all of these other aspects? And the other piece that I didn't put up here was field evaluations. All of this has been done in the laboratory. How do we capture these endpoints in the field? This is not an easy situation to do. You know, we've been talking about semi-field situations, looking at different types of enclosures, but there are limitations to those because then airflow is different, release points are different. You're impacting on all the behavioral pieces that you don't want to alter when you're trying to evaluate these tools. So I think that's one of the challenges for everybody moving forward is how do you capture these other endpoints in the field when they're so much easier to capture in the laboratory. And this is my last slide. So this was kind of a recreation of that crude probability model. And what we're hoping that we can do with these new evaluation tools is to be able to extend that line on the bottom. We're looking at movement away, attraction inhibition, feeding inhibition, but now we need to look at maybe ovipositional site disruption, other types of things that we need to be adding to that bottom line to really get a much better view of what spatial repellents are doing to disrupt vector transmission. And I think that's my last slide. Okay, thank you.